Hello, my name is Dr. Brady Carter, and I've spent my career learning everything I can about water activity and its impact on product safety, stability, and shelf life. I've done multiple webinars, training seminars all over the world, and you may have even seen me in a YouTube video. I also have experience working with all the various water activity measurement methods. I know it can be confusing when trying to distinguish between these different measurement methods. So today, I'd like to use my years of experience to discuss in a very straightforward and honest way the differences between these measurement methods. The approach I would like to take to compare the various methods is to look at 6 important distinguishing factors. The 6 distinguishing factors that we will utilize for our discussion for the comparison of water activity measurement methods includes instrument stability, analysis time, accuracy and precision, maintenance, influence of volatiles, and cost. And first, before we start our discussion, we need to highlight what a water activity measurement consists of. And the thing that's common among all water activity measurement methods is that a sample is placed inside of a sealed chamber, and then water escapes out of that sample. And over time, the headspace will come to equilibrium with the same water vapor pressure as in the sample. So that the relative humidity measured in this chamber, called the equilibrium relative humidity, will be the same as the water activity of the sample. And the methods differ on how they actually measure that vapor pressure or that relative humidity. So if we bring in our 4 most common methods, we have the electrolytic resistivity sensor, the dew point sensor, the tunable diode laser, and the capacitance sensor. And so the commonality between all these measurement methods will be in that they are measuring the equilibrium relative humidity inside this chamber. The electrolytic sensor measures it by tracking changes in the resistivity of an electrolyte solution as humidity changes. Similarly, the capacitance sensor measures the changes in electrical properties of a hygroscopic polymer due to exposure to different humidity conditions, while the dew point sensor measures the vapor pressure inside of the chamber by the dew point temperature, and then the saturated vapor pressure based on the sample temperature, and the two together give the relative humidity or water activity. And a tunable diode laser has a laser tuned to a wavelength that's specific to water, which can then measure vapor density inside the chamber, which then relates to vapor pressure, and also measures the sample temperature to get the saturated vapor pressure. So all these different methods measure in some way or another the relative humidity inside this chamber. But none of them measure it directly in the sample. So none of them is a direct measurement of water activity. Instead, all methods depend on measuring the headspace that's at equilibrium. And so now if we consider each of our distinguishing factors, when we talk about instrument stability, it's really, will I get the same answer every time? And that's influenced by outside factors like the user that's using it and whether or not he's getting the instrument dirty. And in particular, the chilled mirror and even the tunable diode laser depend on cleanliness. The mirror and the infrared sensor can't make the right measurements if they're dirty. And so they are particularly susceptible to those kinds of factors. As well, the tunable diode laser is actually susceptible to pressure changes. So any elevation changes will impact its readings, and in fact, each reading needs to be adjusted based on the pressure. So that means that the two electric property sensors tend to be more stable in that they aren't as affected by the user and potential contamination. That said, the hygroscopic polymer can be unstable when it goes through wetting and drying, successive wetting and drying periods. Because when the polymer is subjected to high relative humidity, it absorbs a lot of that water in the polymer, and it continues to drift. And then when you go back down to lower water activities, it tends to read high. So that can affect its stability. In terms of time, analysis time, the thing that has to happen for a measurement to be taken, there are several steps. One is you have to reach vapor equilibrium, and for each sample type, there is a different amount of time that requires. High-fat samples take longer. Some samples can take less than 5 minutes. Once that vapor equilibrium is achieved, then you can take a measurement on the relative humidity and get the water activity, the equilibrium relative humidity. The requirements that are set to indicate that equilibrium has occurred can also vary. And so this means the only way to track equilibrium is to know that you're at a static state, so there aren't any changes over time. And so what's used is a setting that looks at water activity values over time, and when they start, the variation drops to a certain preset level, that indicates the end of the test. And so the more stringent you set that, the more likely you are to have equilibrium, but it also extends the test time. And so if there are differences between those settings, it will result in differences in analysis times. But let's say that all of those things are the same. So the stability settings, temperature, everything's the same. The electric property sensors will always be a bit slower than the other two methods because they need or require a step where the sensor itself comes to equilibrium with the chamber, and that can only happen after vapor equilibrium is achieved. So with all conditions the same, the chilled mirror and the TDL will be slightly faster than the other two methods. In terms of accuracy and precision, which both need to be considered, the highest level of accuracy reported is for the chilled mirror or dew point sensor or method, as well as the electrolytic method at 0.003, followed by the TDL at 0.005, and then the capacitance usually around 0.01. Now, when we talk about accuracy, of course, we're talking about whether or not the right value is measured versus precision, which means do you get the same answer every time? And really, this can only be measured on specific samples because you have to know the water activity. And so there are both saturated salt solutions and unsaturated salt solutions available for doing these measurements. And accuracy and precision that's reported is always measured on these types of samples under ideal conditions. And so to be able to make sure that they're meeting those specifications, you have to actually do some verification, and that comes to maintenance. And how frequently does that verification need to be done? For instance, on the dew point sensor, it will give very accurate results, but you do have to make sure that nothing's happened to affect that. And thinking back to the stability, again, if there's any kind of contamination on the mirror or the sensor, it will affect the readings. And so in order to be able to achieve the high level of accuracy, you have to verify it and you have to clean it very frequently. And so the maintenance requirements that are needed to maintain that accuracy are fairly high, as opposed to with the electrolytic sensor, which also has a high accuracy. But because the sensor is protected, it's not nearly as susceptible to cleanliness issues. And so the accuracy that it's reported can be maintained much easier without having to have so many times of cleaning or so frequent a verification or making calibration adjustments. The electrical property sensor also is less susceptible to cleanliness issues, but because of its tendency for the polymer's electrical properties to shift and change depending on what's happening, it also needs to be frequently verified and may have to have calibration adjustments as well. When we talk about volatiles, we're talking about the influence that volatile material in a sample can have on the readings. If volatiles get inside this chamber, if the sample has volatiles, then they'll be in the chamber as well as water molecules. And that can influence the results. And in fact, it impacts all of these methods except the tunable diode laser. It is the one method that is not impacted by volatiles at all. So because it has a laser tuned to wavelengths that are specific to water, it only detects water in the headspace. The presence of other volatiles does not cause problems. The electrical properties, the capacitance polymer sensor is the next in terms of its sensitivity of volatiles, because it actually can read with the presence of volatiles fairly well. But continued exposure to these volatiles will eventually change the polymer and cause it to its calibration to be shifted. So even it will be poisoned eventually. The electrolytic sensor is next in sensitivity because it cannot have volatiles in the headspace. It will impact its reading, and if there's certain types of volatiles, it can have an irreversible change. The solution for this particular sensor is for then to use filters to keep out certain types of volatiles. But then with the chilled mirror, the problem with the dew point is that when the mirror is chilled, there will be volatiles that will co-condense on the mirror, and they will impact subsequent readings, and there's really no way to avoid that. So this particular one, the only choice when you have volatiles present, and they're specific volatiles, but if they are present, the only choice is to not use the sensor. And then finally, with cost, each of these instruments have a range of instruments available that cover the cost range from low to high. so that it's not as big of a distinguishing factor, although the TDL tends to be the most expensive technology, while the capacitance method is the cheapest technology. But there are options of each depending on what features they have and the accuracy level within all those price ranges. So if we consider all of those factors now, and we take our discussion and put it in terms of a table, what we see is each of these methods and where their positives and where their negatives are. So for the electrolytic sensor, stability is a very high positive, as well as accuracy and precision and maintenance because of its tendency to not be affected by contamination. But it's a slower analysis time. It will always be slower than the dew point and TDL, and it is susceptible to volatiles. Meanwhile, the dew point gets high rankings for analysis time, fastest method, very accurate as long as it's maintained, but the high level of maintenance required and the fact that certain volatiles it cannot read at all are the negatives for that particular method. The TDL has its highest ranking in terms of analysis time and volatiles because it is the one method that is not interfered by any volatiles, but it gets lower rankings on stability due to its being impacted by pressure, as well as it being quite expensive. And then finally, the capacitance has high rankings in terms of low cost. It's very low cost, has fairly low maintenance, is not as sensitive to volatiles. But where it really falls out is in its analysis time, which is because of its need to come to equilibrium, and its accuracy and precision because of that tendency to be impacted by wetting and drying events that can affect its stability. So as you can see, each of these methods has has their own positives and their own negatives associated with the measurement. And which method is best for you will depend on which of these factors you would deem most important. And there are other factors beyond these, like what is the knowledge of the manufacturer, how capable are they at being able to provide application support and answers. Because once you have your water activity value, the next question, of course, is what do I do with it? What does it mean? How can I utilize it? And so that's another factor to consider. That's not method specific, but it is manufacturer specific in their capabilities of being able to be able to help with those questions. And as I said in the opening, I have many years of experience working with water activity, not only in its measurement, but also its utilization. And what does it mean in terms of product stability and safety? And I hope in the future I have opportunities to help you with those types of questions as well. Thank you.